We're going to determine if the series, the summation n equals 1 to infinity sine of 1 over n cubed converges or diverges. First, let's use test for divergence, which I'll abbreviate by TD. It's the limit as n goes to infinity of sine of 1 over n cubed. We'll evaluate this limit. If this limit is not 0, we immediately conclude that the series diverges. However, in this case, this limit is the same as sine of the limit n goes to infinity of 1 over n cubed. And of course, that's sine of 0, which is 0. And because this limit is 0, test for divergence is inconclusive. The series could converge or could diverge. We cannot conclude based on this limit equal to 0. So we have to try something else. And the one test that will work here is the limit comparison test. And I'll abbreviate that by LCT. Now, brief review of limit comparison test. We have two series. We'll call first one a sub n and the second one b sub n. And the restriction is that an and bn must be positive for all n. If the limit as n goes to infinity of an over bn is equal to L, and L must be positive, so can't be 0, has to be positive and finite, then the following holds. The two series, so either the AN series and the BN series both converge, or the AN series and the BN series diverge. What we cannot have, AN series converging and BN series diverging and vice versa. So now we'll take the series n equals 1 to infinity of sine of 1 over n cubed, and we'll call it the a sub n series, the summation from 1 to infinity of a sub n. And the question is, what should we select for the b sub n series? It has to be a known series, and it has to make the limit be positive and finite. And here, when we have a sine or tangent of something like this, we're going to let the b sub n series be whatever is inside the sine. So the choice for b sub n, summation n equals 1 to infinity of b sub n, in this case is the summation from 1 to infinity of 1 over n cubed, which is a known. This is a p series. Now let's evaluate the limit and see if we can conclude that we can use a limit comparison test. So let's take the limit n goes to infinity, an over bn. It becomes the limit n goes to infinity of sine of 1 over n cubed divided by 1 over n cubed. Now this limit, because n here is supposed to be just positive integers, this is the same as the limit of continuous functions. So it's the same as the limit x going to infinity of sine of 1 over x cubed divided by 1 over x cubed. The easiest way to evaluate this limit, we can use L'Hopital's rule, but the easiest way to evaluate it is with substitution. We let y be 1 over x cubed, and then note as x goes to infinity, y will go to 0. So this limit using variable y becomes the limit as y goes to 0 of sine of y divided by y. And of course this limit is equal to 1, something that you should know. And this is equal to L. It is clearly positive. It is finite. So we can now conclude that both series converge together or both series diverge together. So the summation from 1 to infinity of sine of 1 over n cubed and the series, the bn, n equals 1 to infinity 1 over n cubed, either both converge or both diverge. Now this series we recognize It is a P series with P equal to 3. This series converges, so it converges, and therefore this series also converges by the limit comparison test. Now let's look at a similar series, but the solution is quite different. So let's look at the summation n equals 1 to infinity of cosine of 1 over n cubed. Now, since we just saw sine of 1 over n cubed, we can immediately assume that we should also use limit comparison test here, but that will not work. We should not forget to test for divergence. Let's apply it here as well. When we take the limit as n goes to infinity of cosine of 1 over n cubed. Now 1 over n cubed goes to 0 as n goes to infinity, so this approaches cosine of 0, which is equal to 1, and that's not 0, and by test for divergence this series diverges. So the conclusion here is the summation n equals 1 to infinity of cosine of 1 over n cubed diverges, and this is by test for divergence. For more videos, visit www.mathprepvideos.com.